We have already discussed what happens when we treat an atomic dipole in external magnetic field, and we also know that uh, since in atom we have negatively charged electrons, those electrons, since they are charged and they are continuously in a state of motion in the Coulombic field of nucleus, then it creates its own magnetic field, both from the orbital motion as well as the spin motion of it electron. So we have spin angular momentum, and orbital angular momentum, or the magnetic moment, which gives rise to the magnetic moment. So it is this magnetic moment which is responsible for any interaction between the external magnetic field and the atom. So those intrinsic magnetic moments of an atom, from the orbital motion of the electron or the spin property of the electron, those two dipole moments are the magnetic moments, or the main contributors for the interaction between an external magnetic field and the atom. So atom will interact with the external magnetic field via that dipole moment, via that magnetic moment. And Zeeman effect is one such type of effect which studies the interaction of atom with the external magnetic field. So whenever an atom is placed in the external magnetic field, there is a change in the energy levels of the atom. There's a shift of the energy levels with respect to their ground state. And that shift actually is called as Zeeman effect. So when we observe a shift in the energy levels of an atom, now we can talk of a simplest is hydrogen atom. When placed in the external magnetic field, that interaction or the shift in the hydrogen atom because of that interaction from the external magnetic field, it is called as Zeeman effect. Zeeman effect
Sir,
has,
if we apply, what will happen if we apply electric field?
yeah, when we apply electric field, we will study that too. That's called a Stark effect.
Okay, sir.
Okay, that's called a Stark effect. So Stark effect is a separate topic when we interact, when the electric dipole moment interacts with the external electric field. So the basically dipole moment should be there, like electric dipole moment, magnetic dipole moment, to interact with the external electric and the magnetic fields. So in case of this Zeeman effect, there's an interaction between the external magnetic field and the atom via the dipole moments, the magnetic moments. So magnetic moment we have of two types. One is spin magnetic moment and one is orbital angular moment, magnetic moment. So there are different types of Zeeman effect based upon the interaction. Like we know that S can be 0 for any two electron systems, or it can be 1 for an hydrogen atom, like an hydrogen atom, for atoms, hydrogen like atoms. So that is a singlet state, this is a triplet state. And when we take into effect the interaction of external field, when we consider the interaction of external magnetic field with the atom, but the net spin moment is 0, S is equal to 0. When S is equal to 0, then at that time this is called as normal Zeeman effect. This is called as normal Zeeman effect. And when S is not equal to 0, it gives us anomalous Zeeman effect. So in the first case, and also when we apply some external field, when it is weak, then it corresponds to this state, anomalous Zeeman effect, or simply the Zeeman effect. When B is strong, very strong, it is called as Paschen-Beck effect. These two we will study separately. Today we will discuss only this part. So let us take an atom, suppose a hydrogen atom, and this hydrogen atom we will place in the external magnetic field, and suppose that S is equal to 0. That means there is no interaction between the external magnetic field and the spin magnetic moment of the electron, because there is no spin dipole moment. A special case when S is equal to 0. And if we suppose that B is applied along Z direction, so it becomes BZ. We applied the magnetic field. For example, this is an nucleus, this is an orbit, and this is a BZ here, and we have then L, you have then S, for example, then there's a resultant J, which goes to some, you know, that the vector atom model.
Yes, sir.
Okay, then there is a some L here, sorry, if this is a direction of particular L, this, and then there is a J, this J will go resultant here, from here, from here. So this is L, this is S, this is J. So J will precess around B. Okay, this is called as Lormer precession. When the total magnetic total angular momentum vector precesses around the external magnetic field direction, that type of precision is called as Lormer precession. So we assume that we are applying the magnetic field along Z direction, and since there is an electronic charge, then the charge Q can be represented by minus E. If you remember from quantum mechanics as well as classical electrodynamics, or simply the electrodynamics, you remember that when we place a charged particle in external magnetic field, what will be its Hamiltonian? H, it is equal to, I can write here H naught plus, there is E by 2, it is mu C, you can write MC, but we are taking the reduced mass notation, so I can write 2 mu C B LZ, because S is 0, otherwise there should have been S component for the case of this, plus there is an second order term, which is this x square plus y square. Actually this is treated as a path of the orbit, and otherwise it is R there, it is R there. So this is x square plus y square, since we are taking the orbital motion, so it is a two-dimensional path, so this is why it is taken as the x square plus y square. Now if we take hydrogen atom or hydrogen like atoms, if we take hydrogen atom or hydrogen like atoms, which are very lighter atoms, this interaction, this is a quadratic term, it's a quadratic Zeeman effect. This is a linear, which we will study actually, B dot LZ. Then this term becomes very weak for the case of hydrogen or hydrogen like atoms, and we will drop this term, so the quadratic term will be dropped here. Dropped, and we are left with H will be equal to H0. Can anybody tell me what is H0?
Unperturbed Hamiltonian job.
What will be it exactly?
E by 2m.
This is the Z direction. This is when B is equal to 0, that is unperturbed. and its value is kinetic energy plus potential energy, that is equal to P square by 2 mu minus E square by R in atomic units. So this is the unperturbed part of the Hamiltonian. So if you can write this, if we take that interaction term, this is the interaction between the B external field and the orbital magnetic moment, LZ component of this magnetic moment, orbital motion of the electron, Z component, then we can write it as, we know that mu B is equal to E H cross divided by 2 mu C. Okay, this 2 mu C I can write it as, and we also know that mu L, what is mu L? Because there is actually the mu dipole moment, orbital dipole moment, which will interact. It is actually this interaction. How does the interaction become? When you place an extra dipole in an external magnetic field, then there is a magnetic potential energy which is stored in that dipole, and that is actually mu L dot B. It's actually mu L dot B. So when it is mu L dot B, that mu L is this, okay, and mu L dot, yes, it is E by, it is minus E by, not B there, B will be not here, because we are not, so minus E by 2 MC. So representing this term here, this, in terms of mu B, we can write H will be equal to H naught plus B mu B LZ divided by H cut. So in terms of this is minus mu L dot B, this, because for an electron the orbital angular momentum vector is opposite to B. It is opposite to B. That is why it's minus there. Now, so this is,
सर वो डिले हो रहा है
या एक बार फिर से बोली, क्या बोल रहे हो?
सर बोर्ड जो है डिले हो रहा है सर नहीं कर रहा है
Okay. What to do now? Just try once more. If not working, then let me see what I can do. I can switch the network. Okay. So this is the Hamiltonian for our current problem, that is for the atom in external magnetic field when we take spin angular momentum is equal to 0, S is equal to 0. Is it okay up to here?
सर ये टर्म कहाँ से आई
This one?
यस सर
Okay. I already told you that. One is that you have an unperturbed Hamiltonian, you know all that. There will be added a term which will represent the interaction between the dipole and the external field. This is the external field, for example, B. For example, if this is BZ here, and you have a dipole like this, dipole moment mu L. Okay, then what is the interaction energy, total energy of the system of this? That is equal to minus LB dot B. This mu L is also in the Z direction, but it is in the opposite Z direction. So that is we write mu LB. No need to write this because we're taking the magnitude. And mu L is now equal to this E by 2 MC into LZ. Do you understand?
यस सर
So that is how it comes actually. I have then converted it into mu B. E by 2mc into h cut by h cut. So h cut divided by h cut will remain there and it will become mu b.
Yes, sir.
Now, so this is what you require actually, this. And your problem is now solved, almost it is solved. We know that this H naught and LZ, H and LZ, they all commute with each other. And LZ and H naught, that is what I told you, they commute. So they have a set of common eigenfunctions. We'll treat it quantum mechanically now. Use the perturbation theory. First order perturbation theory. And we have the eigenfunction of psi n l m r theta phi. Because the wave function will be now the function of r, theta, and phi in a hydrogen atom or hydrogen-like atoms. And I can write it as is it okay?
Yes, sir.
Now, in this case, you know that E, N, L, and M is given by I can write it as taking the present condition is it okay? Now separating it,
Yes, sir.
if you this is zero ground state, plus I can write B mu B by H cut. Here we were left with, because this is the only which will change. Now what is this? Anyone?
MH. But
This is not multiplied by B, it is mu B here.
yes, sir.
It's MLH cut actually.
Yes, sir.
Okay. So it is E and 0 plus H cut and entered. I can write it as it is E and 0 plus M H cut omega L, where I can write, because omega L is the Larmor frequency, it is EB by 2 mu C. This is called the Larmor frequency. Omega L. Now, if you see it, we are done. Almost we are done. We don't have any issue in this case now. Our problem is solved. This is the ground state energy. So any energy level with this ground state level is shifted by this much. because of the external magnetic field. And this is the Zeeman shift. Energy shift, or the Zeeman effect. And the important property of this normal Zeeman effect is that when these levels are separated, they are equally spaced. Because what changes here only is M, and this omega L will change because of this B if we change the B, but if we keep fixed B, all the things will remain constant except M. So it means that in this case, the atoms, the spherical symmetry of an atom is broken. And L is now split into the components 2L plus 1, which is actually ML values. So these levels, the shift in this level, any level, the energy change, that delta E is H cut omega L. This is the shift, H cut omega L. And M will just, M is an integer actually here, so it will shift those levels. And it is also equal to B mu B. One of the important property is that this energy shift is independent of L. There is no dependence on this L. So it is still degenerate in different values of L. When we draw the energy level diagram, we should keep in mind that the selection rule delta M, the selection rule delta M is 0 plus minus 1. These are dipole transitions, so generally the selection rules remain 0 plus minus 1. And remember that M equal to 0 to M dash equal to 0 is not allowed. Now, for example, I will give an example here. If we take an atom, or we take any system for which we have different energy levels, this is L equal to 0, L, sorry, N equal to 0, N equal to 1, yes, N equal to 1, L equal to 0, N equal to 2, L is equal to maximum L equal to 1. So I can write it here, or थोड़ा सा हम नीचे लिख सकते हैं, we can write it a bit below here. This is B equal to 0 here. Let's take B is not equal to 0 on this side. And these are the En0 states actually, these. So these are En0 states. Okay, En0 states. And all these. So it is E10, then E20, E30. These are the ground states for a particular quantum number. Now we know that for N equal to 1, L equal to 0, we have M equal to 0. So when M equal to 0, we have only one energy level. That will be E10. Okay, and this B is not equal to 0, so this is 1, 0, 0 state. What is this? This is N and L, that is equal to 1, 0. This is N, L, now we have M, 1, 0, 0. Now N equal to 2, L equal to 1. Take this. How many components will be there? 2L plus 1 components. So L is equal to 1. So these are 3 components. And we know that for L equal to 1, what are the values for M?
Plus minus L.
-1 plus 0 minus
So
1.
this is -1, 0, 1. Now check the degeneracy for L. L is 1. Okay, maximum L. So we have N, L, and M states. So this is -1, this is 0, this is 1. The states for this will be, what will be the states for this? If you write it as, it is 2, 1, L is 1, M is -1. Okay, so we have here 2, 1,
0.
0. There's again 2, 0, 0, because L is still degenerate. Because we know that when N is 2, L is equal to 1, and it has 0 and 1 values, S and P. That is what I write here. This. Similarly, here is 2, 1, and 1, because 0 has been already taken here. You cannot take 0 there further. Now, for N equal to 2, so this 2, 1, okay, it is 2, 0 as well. There is 2, 2. Actually, it is 2, 0, 2, 1, and 2, 2. So I have just the arrangement, there's a ordering is different something in writing. Otherwise, it is 2, 0, 2, 1, and 2, 2. So we have how many components? For D, corresponding to D, 5 maximum possible components. Sorry. And ML is 2, 1, 0, -1, -2. And I can write then, this is N is equal to 3, sorry. It is 1 and 2, 0, 1, 2, not 0, 1. We are N equal to 3. N equal to 2 we have already taken here. So it is N equal to 3. So when N is 3, L is maximum is 2. So we can have ML values 12 plus 1, which is 5. And we can go from 2, 1, 0 to -1 and -2. So we have here, it is 3, 0, 0, 3, 1, 0, 3, 2, 0. Independent of L. Energy will be same, whatever the value of L will be. Degenerate. Now, coming down, it is 3, 0, -1, 3, 1, -1. Here we have 3, 2, -2. Now we cannot take 0 here or 1 here. 3, sorry, this is 3, 2. It should be 3, 2 here. 3, 2, and 0. Yeah, this is 3, 0, 0. 3, 2, 0 is here. 3, 1 is 0. Yes.
1.
3, 0.
Sir, 3, 1 minus 1, 3, 2 minus 1.
3, 2
3,
minus
2,
1.
yes.
3, 2 minus 1. Sorry, this is 1 minus 0 is already there. Okay. Now it is 3, 2 minus 2.
Yes, sir.
Okay. It's not minus. This is only here plus. Now similarly, we have 3, 2 plus 1 and 3, 1 plus 1. This is 3, 2, 2.
3, 1, 1. 3, 2, 2. Yes, sir.
Now what is the energy spacing? Can you draw the energy spacing is here? So this is E10, E20, sorry, not 10, 2. This is E10. What is this? This is E10 plus M is 1 mu B B, because it is plus 1 M there. So what is this? E10 minus spacing actually, this spacing. This is mu BB, this spacing. This is also mu BB. It is this spacing mu BB, this spacing mu BB. And the energy level here is E10 minus mu BB, and this is E10 simply. This is E10 plus mu BB, because M is plus 1 here. Now we will draw that D for n equal to 2. So let me draw it, space it. These are equally spaced. So I might not be correct in drawing, but these are equally spaced. Remember that. For normal Zeeman effect. So this is E30, because n is 3, this level. This is E30 plus mu B and B. This is E30 plus 2. This is for n is 2, L is 0, 2, 1, 2, 2. These are degenerate states, okay? Due to magnetic field, spherical symmetry, that L will be given by ML, and
Sir, 3 1 है and 3 है.
N is 3. Yes, it is 3. Yeah, E30 plus 2 mu B. This is 1 mu BB. Is it okay? Any issue?
No, sir.
Okay. So this is E30 minus mu BB. This is E30 plus 2 minus, sorry, not plus, minus 2. So this spacing, this space is always mu BB. This is always equal spacing, okay? And this is how we draw the energy level diagram for the case, in case of a normal Zeeman effect. And this you can directly convert this, infer from this equation here. This is your final equation. This equation is important, okay? This is actually this and this is being same, because you are applying the magnetic field, so there will be change of that omega L because of that field B, because directly proportional to B. That is why we can write it in terms of this omega L. So if you are not able to draw the energy level diagram with proper indexing, I can say that you might not have understood the concept. So it is important to understand it and then draw this energy level diagram. So when you are able to draw this energy level diagram properly, then I can say that you have understood it. So I think I should leave here. If you have any issues in this or any queries, please inform me and send me a message or call me, whatever you would like. Okay? Quiz Mashiach, thank you, issue.